Deep in space, scientists spot something. It's an asteroid, and it's heading straight for Earth.
100% probability of impact. There was no place else for this asteroid to go.
It's traveling at phenomenal speed, but where and when it will hit and how much devastation it will bring are unknown. Alerts go out around the globe.
We got a warning in the cockpit, then a message came in.
Now, deep in the Nubian desert, they have a mission to search for any remains.
If you get lost and get separated, I tell you, you could easily die.
And what they find in the desert holds vital lessons for the future. For this will happen again. Station 6, deep in the Sudanese desert. Scientist Mawia Shaddad and his driver head out into a ferocious sandstorm. Storms like this appear with no warning and can last for days. Visibility shrinks. The sand blasts any exposed skin. No one willingly comes out into this, but an asteroid has landed out here, and they want to search before everything is lost to the storm. Dr. Shaddad has no idea if he'll succeed, but this is the spot, and he puts down a marker. The extraordinary events which have brought him out here occurred just a few weeks ago. October the 6th, 2008. Astronomer Richard Kowalski arrives for work at the Catalina Sky Survey on Mount Lemmon in Arizona.
I came up to the telescope that evening, and when the sky finally got dark enough, I set the telescope to its task.
The telescope's task is to provide early warning of any threat from the skies. The observatory is one of a network of telescopes spread across the globe.
What we do every night is we search as much of the sky as we possibly can, looking for near-Earth objects, asteroids and comets, which come close to the Earth and may one day impact the Earth. The dinosaurs went extinct because they weren't looking for asteroids and they got hit, and we want to avoid the same fate.
But the task is enormous. On any night, the whole network can cover only about 5% of the sky. The computer divides the night sky into a grid.
There is a little bit of luck in where we decide to observe, even though we are trying to cover the sky in a systematic way.
And that night, Richard Kowalski gets lucky.
On that evening, I had directed the telescope to take 4 images of a region of the sky between Andromeda and Pisces. The way it works is we take a picture of that part of the sky. Approximately 15 minutes later, we take another image.
The software overlays the photographs, and because the stars remain fixed, anything moving becomes obvious.
So the first observation was approximately 10:30 at night. It was clearly a real object. It wasn't a cosmic ray hit or some noise in our camera. So I said, yes, it's a real object.
Richard has spotted an asteroid. Most asteroids, he sees, pose no threat, but it pays to check.
It looked just like any other asteroid, nothing special. I sent off notification to the Minor Planet Center that I had a near-Earth object.
After sending off the details, Kowalski returns to his work. 3 hours later in Boston, Tim Sparr, head of the Minor Planet Center, has just woken up.
I tend to check my email first thing in the morning, so I stumble out of bed and grab some coffee and sit down to see what has come into the Minor Planet Center computers overnight. And I noticed an object had been discovered by the Catalina Sky Survey.
But something was different about this new object. The computers have been struggling all night and failed to work out the orbit of the asteroid. Tim Sparr gets to work.
It took a couple of different tricks for me to actually get an orbit. And when I actually filed that orbit, I got a warning at the bottom of the screen saying close approach coming, and it listed the distance of close approach to the Earth. That was less than the size of the Earth, the close approach distance was. Now that's when things get really interesting.
Tim Sparr's calculations suggest the asteroid is on a collision course with Earth. No one has ever seen this before. But is he right? Following protocol, Tim contacts the world expert on this type of calculation, Steve Chesley from NASA's Jet Propulsion Laboratory in California.
If there's something that's approaching the Earth, that's coming very close or going to hit the Earth, he's the person to call worldwide.
Getting a cell phone call out of office hours from the director of the Minor Planet Center is not the kind of thing that happens every day. He said, "Look, Steve, we've got an asteroid inbound, and it looks like it's on a collision course."
Just sort of no bones about it. "Hey, Steve, I got something that's going to hit the Earth." And he said, "For real?" "Yeah, for real." "All right, I'm on it." So I sent him the positions.
I was anxious to get into the office to verify it.
At the lab, Chesley feeds the tracking data into his computer. And the details of the asteroid's orbit become clear. It is heading directly for Earth.
Never before had I ever seen, even in simulations, the numbers show up as 1.0000. 100% probability of impact. There was no place else for this asteroid to go.
Chesley runs some more calculations. How fast is the asteroid traveling? When will the impact occur? He finds it's hurtling towards us at 45,000 kilometers an hour. And it will be here in only 12 hours' time. For the first time in history, an asteroid has been spotted on a collision course with Earth. But where is it going to hit?
What we have to do is we have to take the trajectory as it's coming into the Earth. We have to find out what time it's getting to a certain altitude and find out what the orientation of the Earth is at that time. And then we figure out what's underneath that position in space. Well, it turned out that it was going to be over northern Sudan, not so far from the upper reaches of the Nile River.
The asteroid is getting closer. It will impact at precisely 5:46 a.m. Sudanese time.
So we worked to get the word out to the astronomers, and then we continued to monitor the progress and the trajectory as the day unfolded, and hundreds of observations from around the world were rolling in.
One group uses the variations in the asteroid's brightness to model its shape and rotation speed. Now the asteroid can be visualized, and it has even been given a name. It is called TC3. And at last, the news gets through to Sudan. Mawia Shaddad, an astronomer at the University of Khartoum, is one of the first people in the country to hear about it.
It could happen anywhere in the world, and it comes here to us in Sudan.
He checks the coordinates to try to pinpoint the location of the expected impact. It's good news. It's a remote spot in the desert in the far north of the country. But there are people there, and warning them is a problem.
It's such a remote area. Hardly any communication exists. You know, yes, I know in America you have your mobiles, you have the net, it does not exist. It's a total different world. And it's not possible.
So in the north of the country, people remain oblivious to the threat that is heading their way. Back in the US, Tim Sparr is attempting to answer the critical question. How big is the asteroid? He bases his calculations on observations of its brightness. How much damage will it cause?
Immediately, I'm hoping that I was going to see a small number on the size, and I did. Had I looked and seen that this was a 500-meter object, I'd have been devastated.
It appears the asteroid is about the size of a truck and weighs 80 tons. It won't be an extinction event, but it's large enough to make a very big bang. In space, satellites focus on the predicted area in the desert. And in the impact zone, Isa Ali Hassan is leading his camels in search of food. And then, at almost the exact moment predicted, the asteroid arrives. After hurtling through space for millions of years, it is on its final approach. TC3 hits the atmosphere at 12 kilometers per second, generating temperatures as hot as the sun. It begins to break up and then explodes with the force of a small nuclear bomb. Luckily, it never reaches the surface. The detonation is so high, no one is reported hurt. One quick-thinking local man even manages to record the smoke from the explosion on his mobile phone. High above Earth, satellites also captured the moment the asteroid exploded. For the first time ever, an asteroid has been seen in space and tracked all the way to impact.
I guess I just figured that it wasn't going to happen in my career. I didn't really think we'd discover something that would hit the Earth, a day later or a week later.
But it could easily happen again. There are millions of asteroids in our solar system, in the asteroid belt between Mars and Jupiter. Even more objects circulate in the Kuiper belt beyond Neptune. Within these crowded belts, objects frequently collide. At any time, one of the pieces can be pulled by Jupiter onto a course that perhaps millions of years later will impact with our planet. And knowing what an asteroid is made of, how solid it is or how light, could be critical if we're to defend ourselves in the future. After the impact of TC3, asteroid specialist Peter Yeneskis is desperate to try to collect fragments. They're called meteorites.
I mean, here was an opportunity to collect some meteorites on the ground and to link them directly to an asteroid approaching us, to an asteroid that was observed in space.
They know what TC3 looked like in space, so any fragments will help them understand the composition of other asteroids out there. But are there any samples to find?
I didn't know what the circumstances were in the country. I didn't know whether we could travel out of Khartoum and go to the area where the meteorite may have fallen.
Yeneskis makes contact with Sudanese professor Mawia Shaddad. He's already planning an expedition himself before any meteorites are lost to the desert. And so, just a few days later in Khartoum, Shaddad and Yeneskis join forces and finalize an expedition to search for remains of the asteroid.
I did not know exactly what clothes to bring, whether we need lots and lots of water, whether it would be hot in the desert or cold. I had no idea.
Loaded with provisions for 6 days, they drive out of Khartoum, bound for the Nubian desert, one of the most remote areas in Africa. It's a 2-day journey through the heat and the dust. They're following NASA's coordinates, and they'll need them in this vast and empty terrain. As they get closer, they start to meet people who have first-hand knowledge of the event.
كان في كويكب دخل وانفجر فوق عمل ضوء شديد هنا يدي في جهة الشمالية على محطة 6.
ايوه
انت ها شفتوا شنو؟
لقينا نور باهرة شديد في السماء زي الدائرة كبيرة كده. لما الصحيح لو عيناه لقيناه حاجة كبيرة خالص طوالي خفنا منها قمنا دخلنا البيوت جوا. تاني ما عرفناها مشت فين وقعت كياي وقعت هنا غايته بس ثاني فتنا منها طوالي خشينا البيت.
En route, they are joined by a group of 50 students from Khartoum University to help with the hunt. They'll need every one of them. They're heading for a remote outpost on the railway, deep in the desert called Station 6, close to where the asteroid exploded. This will be their base for the expedition. Yaniskas gets straight to work, attempting to calculate the height of the explosion using the mobile phone picture of the smoke. He works out the explosion was 37 kilometers above the desert.
I remember having this sinking feeling in my mind that nobody had ever recovered meteorites from an explosion as high up as 37 kilometers.
The chance of finding any fragments from TC3 now seems even slimmer. In the morning, the expedition wakes to find a sandstorm has hit Station 6 overnight. Though the team prepares to search, everybody knows it's futile. Sandstorms like this arise with little or no warning and are incredibly dangerous. With only 6 days' provisions, losing 1 day to a sandstorm is a huge setback. And the weather looks like it's getting worse.
I woke up this morning really psyched. I thought this was the day. We're going to find lots and lots of meteorites, and look at this now. It's just terrible. I'm afraid that these winds, the big storm we're having now, will wipe out a lot of the traces of the pit that was created when the meteorite fell on the ground.
A lot of those pits are going to disappear.
Waiting for the storm to blow out is nerve-wracking. At last, after many hours, the wind subsides. Now they can start the search. Any pieces they find could be critical in defending ourselves against asteroid impacts in the future. They line up along the track line, the area under the path of the incoming asteroid. The searchers walk nearly 20 meters apart, in a line that stretches a kilometer. They're looking for any unusual stones, or the pits in the sand they make when they land.
We had only 2 hours today, unfortunately. But oh man, I'm hoping so much that somebody here yells, "Yeah, I found one." That would be really good for morale.
But the day ends empty-handed. Everybody now has a clear idea of the huge task they face.
Hello, يا شباب. أمرك اشربوا برا، أمرك اشربوا برا.
The next morning, Dr. Shaddad is keen to get going.
We're trying to be as early as possible because we worried the wind may pick up around 10 o'clock and then we'll have the same disaster as yesterday.
The weather looks clear, and everybody wants to get out there to be the first to find a meteorite. Shaddad has organized the students to search as much as 10 square kilometers a day. They're eager to get started. The trouble is, they've never seen a meteorite before.
Any dark stone or black stone, you get cold. You got a 1 kilometer people spread walking, and you have to rush from this to that, to this, to that.
The reality of searching for meteorites in the desert means concentration and lots of walking. Then, after hours of searching and many false alarms, a distinctive black stone.
Oh. Who found it? Richard, congratulations. The moment I saw it, I knew it was a meteorite. It had a beautiful little fusion crust on it. I just couldn't believe it. I take a picture of the coordinates and the meteorite, so I know which meteorite belongs to what coordinates. That's right. And I take a picture of the person who found it, so that if, in case we lose any of that information, we can still give credit to the person who was very lucky.
Now they know they are on the right track. And then they start to find more.
In group 4? Okay, we are on our way. Just like finding a needle in a haystack. The area is huge. But this is it. Who found it? Hey!
Oh, thanks. Thank you.
Ionescus identifies the meteorites from evidence of melting on the outside, called the fusion crust. It's a result of the searing heat the asteroid endured when it ripped through the atmosphere.
What I have in my hands here is a piece of an asteroid, which means it comes from space. This is a sample of a celestial body that NASA would spend a lot of money trying to bring to Earth. A lot of money. It would be very difficult. And if you would design a mission to go to an asteroid and collect a sample, you would collect maybe a gram, a tiny bit. This really takes the pain away from yesterday.
The following day begins early, and the search moves a kilometer further south. But driving anywhere in the desert is far from easy, especially in a bus. The plan to move south has paid off. They're finding even more meteorites, but the material is very different. Some pieces are crumbly and fragile.
Yeah.
Others are quite solid.
So this is very exciting. This really suggests that we are finding material that is coming from certain areas in the asteroid.
It appears that TC3 was a mixture of materials, some unlike anything that Ionescus has seen before.
God! Is that amazing? What is that?
You're telling me?
I don't know. It looks like a meteorite because it has the sort of fusion crust, the glistening shine to it.
Everything. What's the
But
color?
it glistens green. Beats everything. We've seen some strange things, but this is really strange.
Piece by piece, they're managing to build a picture of asteroid TC3, and it's a very peculiar object. Later that night, in the tiny shop at Station 6, they discover another puzzle is emerging.
So our initial searches were focused on the area from the track to the 1 kilometer above the track.
Most of the fragments are turning up a little away from the predicted track of the asteroid.
Maybe a little bit more, maybe one. But now we found today that most of the meteorites are found south of the track line. But if you just want to be efficient at collecting material, then you would focus on the densest part here.
It suggests that the path of the asteroid was perhaps a kilometer further south than predicted. But why? Did NASA get it wrong?
This part is supposed to be the middle of the meteorite track. So this is where most of the pieces have to be found.
The number 290. We are now in the thick of it. This is where the meteorites fell, from here and then all the way down track back to the railway. So now it's just trying to keep up with students. As you can see, there's several waiting. So I'm off to number 220.
Now they're finding scores of meteorites. But eventually, the finds begin to run out.
Peter, we're reaching here 3.5 kilometers and the number of findings are getting lesser.
Okay, can you perhaps have the students walk maybe half a kilometer further, so we are certain that there are no further fragments found?
With the expedition drawing to a close, Yaniskas and Shaddad are left with some puzzling questions. And back at Khartoum University, they begin to search for answers. They start by measuring the weight and density of the samples.
4.41 grams.
Rough measurements show the density of some pieces is extremely low, lighter than solid chalk. But the pieces are not uniform.
Every time when I unwrap one of these parcels, it's like Christmas. You find something that is brand new. Look at this.
It's clear that TC3 was an extraordinary object, a fragile mixture of different types of rock. But how was it made? And how typical is this of the asteroids we might need to defend ourselves against in the future? They agree to collaborate on the testing of the samples, and some are sent to the US. The samples arrive at the Carnegie Institution in Washington, D.C. Here, Andrew Steele begins to investigate the strange makeup of the asteroid. He's never seen anything like it.
Basically, it looks like a conglomeration of what your breakfast would look like if you cooked it for about 2 days on a gas stove. It's completely cooked beyond any recognition.
Using a powerful laser spectrometer, Dr. Steele focuses on the carbon content of the asteroid.
The width of this peak is an indication of how high a temperature this meteorite went through. And basically, this peak here is indicative of a temperature of around about 1,000 degrees centigrade, which was, you know, a good 150 to 200 degrees C hotter than anything we've seen before.
And these samples come from the inside of the meteorite, which shows the heating occurred when the asteroid was formed. Steele decides to take a closer look at the material under a microscope. He mounts it between two glass slides and makes a key observation.
When I took the slide off and put it back into the microscope, then I could see scratch marks cut into the glass. There are very, very few things as hard as glass or can leave a mark in glass.
He trains the microscope on the grooves cut into the glass.
By following those scratch marks, the particles that caused them, I started to analyze those, and out popped a diamond.
The sample contains diamonds, and these diamonds still show evidence of the sudden and enormous pressure which formed them.
If you were to be buried about 6 kilometers into the earth and piled all that rock on top of yourself, that's roughly the amount of strain that those diamonds are under. We've analyzed hundreds of meteorites, and basically this meteorite stood out immediately as something that had gone through quite a cataclysmic event.
The history of high temperatures and pressures suggests that asteroid TC3 was formed in an enormous impact. Its strange composition seems to be the result of a collision between two asteroids, which produced many smaller pieces. But how likely are we to encounter an asteroid like TC3 in the future? That's the question which Janice Bishop at the SETI Institute is trying to answer. She is looking at light reflected off the pieces to compare the measurements from TC3 with the asteroids we see in space. Asteroids are grouped into families called classes, depending on their appearance.
So over here, we have spectra from a number of types of asteroids. The light green spectrum is the meteorite we just measured, and the dark green spectrum is the F-type asteroid. And you can see the meteorite provides the closest match with the F-type asteroid in dark green.
The measurements from TC3 are almost identical to those from F-class asteroids. So Bishop concludes that TC3 was an F-class asteroid itself. Many of these dark asteroids are known, and she now suspects that most will be similar to TC3. And amazingly, by studying TC3's orbit, they can identify another F-class asteroid, which might be a far greater threat.
We can follow all the way back to the very area, the very region in the asteroid belt where this particular material came from.
Starting from TC3's trajectory as it approached Earth, they can wind back the orbital clock to see where it may have come from. It leads back to one particular F-class asteroid. It's known as 1998 KU-2. This gives them an astonishing insight into both TC3 and a possible new threat. Millions of years ago, two huge bodies collided and broke up. One piece, TC3, spun off and would eventually arrive on a collision course with Earth. But close behind was KU-2, and its orbit is expected to evolve in the same way. KU-2 is 2.5 kilometers across. If it's ever on a collision course with Earth, it will pose a threat to our civilization. It will need watching. Mark Boslow is probably the world's leading expert on aerial asteroid explosions. He's been using the data about incoming asteroids to model what occurs on impact. He works at the Sandia laboratories in New Mexico using their supercomputer to work out how and why certain asteroids explode in the atmosphere with such force.
We don't normally think of energy of motion as being powerful, but when you're moving at the speed of an asteroid, the amount of energy in a ton of material of the asteroid is much greater than an equivalent ton of high explosive.
Mark Boslow has shown that with fragile, low-density asteroids, the pressure of the atmosphere on impact can cause them to explode.
Because they fall apart, they can explode very violently. And if they're big, that can be like a nuclear explosion.
Now, for the first time with TC3, he can compare his simulations with what actually happened.
Here's a case where we actually have the pre-impact properties. I knew that the impact angle was 20 degrees. I knew that the velocity was 12.4 kilometers per second. I had an estimate of the mass, so I could use that to initialize my simulation and actually simulate something that really happened.
Boslow hopes that modeling the impact will explain what happened, why TC3 exploded so high, and why it appeared to be off track. Eyewitnesses had talked about several explosions.
It was some sort of pulsating light, but it was fairly strong.
In reality, just like rocks and dirt clods, asteroids are really complicated. You know, they have hard spots and soft spots. They may have very unusual shapes. They may have pieces that will break off as they enter the atmosphere. So in reality, it's not a simple single explosion. It's a breakup event. It's a lot more complicated than a lot of us assume.
TC3's complex structure and shape meant there was more than one unpredictable explosion, and its very low density caused it to detonate high in the air. The analysis suggests that taken together, these factors could explain why the asteroid appeared to be off track.
I mean, when you think about it, it's absolutely remarkable that JPL got so close and so perfect timing to this explosive event. We didn't know what altitude it would explode at, because that requires information beyond what they had.
Boslow is now modeling much bigger objects of similar composition to predict what we can expect if we ever see one coming. An F-class asteroid just 40 meters across would explode with the force of a large hydrogen bomb. What TC3 makes clear is how critical it is to know what an asteroid is made of if we're to understand how it will behave. And that has implications for how we defend ourselves against an asteroid. One man who's spent a lot of time thinking about that is David Dearborn, a physicist at the Lawrence Livermore Laboratory just outside San Francisco. Dearborn's convinced the best way of deflecting an approaching asteroid is with a nuclear detonation, and he's been using tests performed in the Nevada desert to calculate the explosion required. These tests were conducted to establish if nuclear devices could be used for peaceful purposes. 40 years on, Dearborn is trying to put the tests to good use. His research suggests it's vital to know what the asteroid is made of. Okay, this is a pillow, not an asteroid, but it's extremely low density and demonstrates how difficult it would be to deflect.
Shooting at the pillow has almost no effect. The bullet just goes right through, hardly delivers any momentum at all, and sort of an impactor or even setting off a nuclear explosive to have gas to push, you'd be very concerned in this case about getting enough push. You get a much bigger push if you have something like densely packed earth or sand or gravel.
A denser asteroid would behave very differently.
The hard object provides some resistance to the projectile as it goes through, and so a lot of the energy in the projectile gets deposited in the body, and that's what would happen if the asteroid had a dense surface.
But some asteroids, perhaps like TC3, could just break up into smaller pieces without deflecting. This could actually increase the threat.
The reaction that an asteroid would have to either an impact or a nuclear explosive really depends a lot on the mechanical properties of the rock. And is that rock fragile? Is it already a lot of rubble and very loosely set together? Or is it more tightly packed? And things like TC3 are giving us a better connection between what we see in space and what the actual rocks are like that we have here on the Earth.
Dearborn believes that as long as he knows what an asteroid is made of, he should be able to design a suitable nuclear device to deal with it. But he would need time.
The effect of letting nature take its course may be a lot less desirable than setting off a nuclear explosive. It's technology we have in hand. It's not a thing where I'm saying, oh, we need a great research project to go and develop a new type of nuclear explosive. No, we did that in the past. We have that knowledge, and we can use it. But it's not an off-the-shelf item. We can't go down to Satellites or Us and pick one up.
The nuclear approach isn't a danger to anyone. In fact, we might say it would be good to get rid of a few of our extra nuclear bombs that we have on Earth. So the danger is simply that it won't do the deflection properly, that this explosion will interact with the object in a way we don't understand, perhaps break it apart instead of deflecting it.
After TC3, asteroid expert David Morrison believes we should be doing more to find out what any threatening asteroids are made of. And there is a big threat out there. An asteroid large enough to cause widespread devastation.
Apophis is a specific asteroid about 300 meters across that could wipe out a country if it hit. And it's so interesting because it comes very close to the Earth, visible to the naked eye crossing the sky in April of 2029, and it has a small but not zero chance of coming back 7 years later and hitting. We definitely don't want that to happen.
Morrison feels we should be planning now to find out what Apophis is made of, in case we discover in 2029 that it's going to hit us.
If you really want some honest truth about an object like Apophis, then you need to send a spacecraft, a reconnaissance spacecraft, to go there, fly in formation with the object, and study it at close hand.
If we plan such a mission to Apophis now, then we'd have time to deal with it if we eventually find out it's on a collision course. But perhaps the biggest lesson of TC3 is that in other cases we may have no time at all to plan a defense. We now know that we have the means to detect and track small asteroids on their final approach to Earth.
And that's what happened with TC3. We found it, we computed its orbit, we analyzed the impact probabilities. Well, this time it was different. This one was on an impact trajectory, and so that analysis and chain of events shows us that TC3 has shown us that we can do this job.
The wonderful thing about TC3 is that we have suddenly realized that the existing telescopic search telescopes that we have can find these things, objects like TC3, as they come in.
And as the people searching the skies know only too well, there are thousands of small asteroids. And that's what we're most likely to have to deal with. And from this year, there may be a greater chance we'll detect one. The Sky Survey network is being upgraded. More money will be spent searching more of the sky for more of the time.
I actually hope not to find the one that's going to wipe out civilization, because that would be a really bad day.
But a small asteroid could be a pretty bad day for someone. Clark Chapman is a space scientist at the Southwest Research Institute. He believes that after TC3, we should be looking at the whole asteroid threat differently.
For the last decade or more, my colleagues and I have been worried about asteroids larger than 1 kilometer in diameter. We just didn't think that these small telescopes in the Space Guard survey, and they are rather small telescopes, would be capable of seeing smaller asteroids.
Now we know we can spot them, but probably only as they approach Earth.
The analysis never was done that we would see things on their final plunge to Earth. The death plunge is a totally new concept for the telescopic searches for asteroids.
It's likely we'll only get a few days' warning, perhaps a week.
Because you can now warn people. If that were a larger object that was going to hit, if you give them a few days of warning, they'll get out of the way and they'll live.
Imagine the warning has gone out. A 30-meter object is headed towards San Francisco and is due to impact in 1 week. It seems to be another F-class asteroid, perhaps a big brother of TC3, from the same asteroid collision.
If an object like this exploded over San Francisco, it would wipe out everything north of Market Street. It would take out the bridges, it would take out the buildings. You'd have to evacuate.
Many scientists believe that emergency management teams should now be preparing to deal with an asteroid threat like any other impending disaster. As the city waits for impact and a devastating explosion, the population is given clear notice, and the streets empty. People leave in any way they can. Since the birth of the solar system, Earth has been hit by asteroids, large and small. Now, for the first time, we can see them coming.
What we've learned from TC3 is that when a small asteroid is headed toward the Earth, there's an excellent chance that we can provide some days or weeks of warning to people, get people to evacuate, get them out of harm's way. Maybe they can be 100 miles away and look back as the asteroid explodes, but they'll be safe.
With advanced planning, when the time comes, we could now save thousands, even millions of lives.